you just look at the pink sheet, the oxidation of the estradiol to estrone, which is a common example of an alcohol oxidation. Okay. By the way, phenols are not oxidized like regular aliphatic alcohols. Okay. They can be oxidized, not as readily, although sometimes more readily. But in this case, the secondary aliphatic alcohol is being oxidized. The carbon now has 2 bonds to oxygen, yes, but also a number of H's. We're removing 2 H's. Okay, 2 H's, minus 2H. Okay, sometimes it's like this. Not H2, but just 2 H atoms. Because we're removing an H from here and here. And when you remove H's, that's typically an oxidation. On the other hand, if you add H's, okay, coming this way, that would be an oxidation. OX, or sometimes just O, indicating oxidation. I'll be going the other way. We're adding H's, one here and one there.
Do you mean reduction? Yeah. Going the other way, isn't that a reduction?
I'm sorry. Yes, it's reduction. Because that's an H. Usually you denote reduction with H. And oxidation with an O, like an O or an OX. And that's what threw me there. I had the H's up there, so I wanted to put the OX. Yes, the other way is reduction. Okay, so we saw here primary alcohols give aldehyde initially, but the aldehyde can be further oxidized to the carboxylic acid. That requires oxygen. I'm sorry, well, it requires an oxygen, but the oxygen comes from water. Okay? That's where the other oxygen comes from. Secondary alcohol gives ketone just by removing the 2 H's and putting in the pi bond between the C and the O. Tertiary alcohols cannot be oxidized in this class. Ketones cannot be further oxidized in this class. Aldehydes can be. The big 3, such as potassium permanganate, sodium dichromate, etc. The big 3 will convert primary alcohol all the way to carboxylic acid. And so you don't isolate the aldehyde. And on one of the sheets it's shown in brackets. We will see a reagent where you can stop an aldehyde though. Okay, we sort of have 2 handouts here. The pink is sort of the outline with some problems, and then the blue is sort of handwritten sort of notes. Big 3. The big 3 oxidizes primary all the way to carboxylic acid and secondary to ketone. No reaction to tertiary. Mechanism. Let's look at a possible mechanism so it's just not magic. We take this alcohol, all right, and let's see if we can get to this oxidation product, removing the 2 H's. Let's consider metal. Let's say maybe metal 2+. The metal could be a variety of oxidation states, very generic. Okay? The metal might be manganese, chromium, and other things, copper. And if we can consider maybe these electrons here, and let's keep track of these electrons here. Attack that. Attack your metal, and we get to something that looks maybe like this. The metal is now only 1 plus. That's a plus. There's an H here. Now if we have water, okay, let's just make sure we... Where's this lone pair at now?
Bonded to the metal.
It's the bonding pair to the metal, okay? Now what if we do this? That takes the H, these electrons move in and kick off the metal. What type of mechanism does that look like?
It looks more like an S and
Looks a lot like a
SN2.
No, an E2.
no, E2.
I mean E2.
Looks like an E2. Yes. What does this give? Well, it's going to give, we're now putting a double bond between the carbon and the O. There's an H remaining. Okay, lone pair remaining gives that. And then you just lose the H plus. Something takes the H. Okay? There's got to be a minus with that metal plus. Okay? And that's how it can be. Now, two things. First off, E2. I thought E2 required strong base. Yes, it does when you're making a traditional E2 mechanism and making an alkene. This looks like an E2. Is this the exact mechanism? I'm not saying it is. I'm just trying to give you something so it doesn't look like it's magic. Okay? If you can follow the arrows, it's good. But what is the fate of the electrons, though? Lone pair. What should we draw on the metal over here? What does the metal now have as a result of this arrow?
Natural pair.
Yeah. And the charge of the metal should now be neutral. Look at it. The metal went from 2 plus to neutral. What happened to the metal? It got reduced. Something had to be oxidized. Yes, this was oxidized. Look at the lone pair. This molecule had 2 electrons. And it lost them. The metal now has the electrons. So when a molecule loses electrons, what do you call that? An oxidation. And so we see the traditional way of viewing this as an oxidation. It lost the electrons to the metal. Okay? So, it's not a precise mechanism, but a little bit of looking at it so it's not magic. Yeah? All right. And again, a variety of metals can do this. Now, how would you get the carboxylic acid from such? Importantly, water is required, and with water, you get this, okay? H2O added. Water adds to carbon, electrons up, and then do a proton transfer. That's all it is. We will see this later. This is called a hydrate. More specifically, a carbonyl hydrate. It's because we just added water to the carbonyl. And when you add water to something, you call it hydration. Okay? We will see that. The hydrate is there. Now, when you do the oxidation, just do it between one CO. Remove the H, remove the 2 H's, put the double bond here, and that's going to give carbonyl, same type of mechanism, but carbonyl OH. And that's a carboxylic acid at that point. Okay? So that's just your oxidation. The exact same mechanism over here. But you had to have the water first to form the hydrate, which is then oxidized. Okay? And that's easily formed from the aldehyde. You can't do that with a ketone because you'd have to cleave. You don't have an H on this carbon any longer. And so it can't oxidize again, not by standard chemistry we're looking at. Okay, we talked about the Jones oxidations test, the chromium orange turning to, that's chromium 7, I think, and ultimately becoming chromium, was it 4? Yeah.
3.
Chromium 4 initially, and then it goes to chromium 3?
Mm.
Yeah, okay. Chromium 3 being, what color?
Blue.
Blue? Okay. And that visual change in color there can be evidence that a oxidation took place. Okay, simple predictive product. Okay, just look what we got here. We have an alcohol. What are alcohols? What's a common reaction of alcohols? Oxidation. I mean, I have a few different ones. What is this?
The big three.
It's like an oxidant. You got to recognize your oxidants. You got an alcohol. You got an oxidant. What are we going to get here? A ketone called cyclohexanone. So some reactions you just have to kind of just recognize them, okay? And this is a little bit less mechanism. Okay, again, we looked at it a little bit. But a little more memorization, okay? Alcohols, oxidized, what type of products do you get? What reagents do this? Okay. Down here, primary alcohol. Looks like another one of the big three. The big three often used with acid, especially the chromium reagent. Product here. Well, you can think about it stepwise. If we make this a carbonyl, remove two H's, we get aldehyde. Now I draw the H in of the aldehyde. There's two here, right? Two here. But we're removing those two. Carbonyl here, one H remains. There's the H that's remaining. Because it's an aldehyde, I draw in the H, and I recommend you do as well. Okay? Is that the final product?
No.
The big three oxidizes it all the way. What do you need here for this oxidation, other than the metal?
Water.
Water. Okay, there you go. It's aqueous. Water's there. It's going to make the hydrate. Okay, this is going to go all the way to basically what is the final product?
Carboxylic acid.
This becomes carboxylic acid. Don't lose track of your carbons. 5 carbons, 5 carbons. Yeah? Yes. You have to just go through this. Okay, what if you wanted to stop at the aldehyde? Can you?
Yes, using something else.
You can, but not with the big three. Big three won't stop at the aldehyde. One reason being, the big three, you always have to use water with the big threes. They're typically always aqueous. If you can do this without water, it will stop at the aldehyde. How can you do this without water? Other reagent. Something like PCC. If you use PCC, it's the same starting material. You'll get the aldehyde. Okay? We'll look at PCC. Dichloromethane, just a common solvent. What is PCC? I'm thinking it's in the other handout. Blue. It is a chromium reagent. Stands for pyridinium chlorochromate, PCC. It's got chromium trioxide chlorine molecule, and that's an anion. And then it has a protonated pyridine as the cation, and that's called pyridinium. Pyridinium chlorochromic. But this reagent can be used without water. And you can use it in an organic solvent such as dichloromethane, and it can be dry. Dry enough that you can get a good yield of the aldehyde because there's no water to form the hydrate, and thus you're not going to oxidize further. All right? Now there's variations of PCC, especially in the older books. You know, nowadays they may have just gone with PCC. But you may see PDC or Collins reagent. You can look these up. They're going to be slight variations of this. All right? I'm not going to show you these. I'm just telling you, perhaps you may see them. I don't know. Sort of, these reagents are sort of not seen as much these days in textbooks. All right? Just variations if you happen to see that. So you take this alcohol. One of the big three, you're going to get the carboxylic acid. But if you use PCC in some dry organic solvent, aldehyde. It will stop there. Now, can you oxidize an aldehyde to the acid? Sure. The big three is doing it here. It's an intermediate here, and the big three just oxidizes it. So you could see this as a separate reaction. Aldehydes being oxidized to acid. What will do that?
Metal?
One of the big three will do that. Okay? One of the big three will do this. But we also have a unique reagent that will do it. And about the only thing that will do. Silver metal. Silver ion will do this. But silver ion won't do this oxidation over here. Just about the only oxidation I'll ever see silver ion do is oxidizing an aldehyde to the carboxylic acid. It will do it. Now, this can be also a test. First off, it's called the Tollett reagent because it's a complex. You have to use it with some ammonia, NH3, aqueous ammonia, which ammonium hydroxide. The ammonia helps make the silver soluble. And so it's sort of a mixture. It's called the Tollett reagent. But the Tollett test, this can be used as a test because when you do this, you oxidize this and you reduce the silver to silver metal. Okay? The silver gets reduced. But the silver metal will separate as a metal because metals aren't soluble. And in some cases, if it's done just right, the metal will kind of coat the flask and it will form a mirror because the silver will be reflective enough that you can see yourself. And it's called the silver mirror. Sometimes it may instead be sort of colloidal and not really be reflective. But it can. And if you get that silver mirror, that means that you have reduced your silver, and that means you must have had an aldehyde. And what might we be comparing or thinking we have? This is a good test to distinguish between aldehydes and ketones. Both are kind of simple, standard carbonyl compounds. The IR may look very similar. Both have carbonyls, although you can distinguish an aldehyde by IR. Carbon and NMR, they'll both show carbonyls about 180, 200. I don't know if I've got an aldehyde or ketone. We'll do a Tollett test. Which one will give a positive test? That means which one will give the silver mirror?
Aldehyde.
Aldehydes. Ketones cannot be oxidized. Thus, certainly not by silver. Since a ketone can't be oxidized, the silver will not be reduced. Okay? Tollett's test is a good way to confirm aldehyde. All right? That's our third wet test. Lucas, Tollett. What else do we have? Jones, oxidation, right? Color, the one we just talked about earlier, right? Okay. Yes, aldehyde ketone. For secondary alcohol, we're going to stop at the ketone. By the way, you could use PCC for this. PCC will oxidize either primary or secondary. But there's really no need to use PCC here because the big three is not going to further oxidize the ketone anyway. PCC is probably a little bit more expensive. So why use PCC down here when you don't have to? There's the, on the pink, there's the Collins. Okay, ketone or ester. You know, they're all carbonyl compounds. Do you think you got a carbonyl compound for some reason? You can use tolerance to help narrow it down. Right? Now in biochemistry, you'll see a test called the Benedict test. Very similar, except it uses copper instead of silver. And when the copper is reduced, I've never done this test, but it turns very brick red. Okay? But only an aldehyde will do this. Because essentially, the aldehyde is being oxidized, but at the same time, you could say the aldehyde is reducing the metal. And only an aldehyde will reduce silver ion or copper ion now with the copper, you're going from 2 plus to 1 plus. Because that's actually copper 1 plus. So it is a reduction, but it's not forming copper metal. It's still an ion. All right, so you probably see that in biochem. It's just more used by biochemists, more classical for those guys. Okay, the other thing we need to look at here with this material is oxidation of alkenes. All right. I'm probably going to have the blue here, and I'm going to kind of read off the pink. Some reactions of alkenes. Now, some instructors actually cover these reactions in organic 1 when alkenes are covered. I don't. Do you remember the alkene puzzle I gave you? Which I might give you again. There were 3 on there that I said we're not doing until organic 2. Okay? Well, those are here now. Okay. One reaction of alkenes is to oxidize the alkene to a cis-vinyl diol. Vinyl, 1,2. Cis diol. Diols are also known as glycols. Sort of a slang name for a diol. ethylene glycol, antifreeze. Okay? One of your big three, KMNO4 will do this. Alkene diol. Okay? Each carbon is being oxidized. How many bonds to a more electronegative atom does this lower carbon have? 9. Now,
One.
one, it's been oxidized. So has the other carbon. 2 carbons of the alkene have been oxidized. I'm thinking the manganese probably gets reduced. All right. Mechanism. Let's see if it's reduced. Manganese, permanganate can have a structure like this. Okay. This is sort of like a Diels-Alder. It's a cycloaddition. It is a 2 plus 3. I haven't had math in a long time, but I think that's what?
5.
I think it's 5. Okay? You're making this 5-membered ring here. If you follow your electrons, it should give that 5-membered ring. It's a cycloaddition reaction. This is called a manganate ester. It's not stable. So maybe you put brackets around it. Not stable. It will then break down to your product, diol. Basically, this gets cleaved and this gets cleaved. Now, I said water. I'm not really sure if water is needed here because the fate of this is MnO2. MnO2, all right? The fine details not here. We're not going to look at fine details for these mechanisms. Again, I'm giving you enough to sort of so it's not pure magic. Let's look at the manganese. Over here, it's manganese 7. The manganese here is now manganese 4. So you see the manganese has been reduced. Carbons of your alkene have been oxidized. All right? But is cis, because when you make the 5-membered ring here, this reagent, the permanganate, comes in from either the front, and both bonds are going to be like this, cis, or from the back. All right? Because this is either front or back, not side, and that's why the 2 bonds are cis to the oxygen. And so again, there's some sort of a little bit of memorization in these reactions. Prompting, okay? Alkene, oxidation, what type of product? All right. That's going to be a cis diol. Big 3, alkene. Okay. There's no alcohol here to oxidize. It's the alkene being oxidized. And the product here is, what's the product? Cis diol, right?
Mm-hmm.
All right, you just have to know your prompts. Cis diol, and the methyl here would be like that. Plus what?
Enantiomer.
Plus enantiomer, because the enantiomer would have both OHs back and the methyl core. Because the reagent can attack from either side. And you'll get a 50-50 mix. Question?
Is it just, sorry, is it just potassium permanganate or any of the big 3? Because you said.
Permanganate is very common here.
Okay.
Theoretically, there's many oxidants can do it. On the next page, we'll see an osmium do this. Sorry, you were...
Is the one above it, is the ester, the not stable part, is it missing a lone pair?
Excellent, yes. Yes. How do you notice that along there? That arrow right there means something to you? Yeah. Yes. I didn't show the lone pair, but it is there. If I see this arrow, what does this arrow mean? Yes, that's where that lone pair came from. Okay. Now this product is not chiral, right? Plane symmetry, there's no enantiomer there. You could show the 2OH is back. It'd be the same compound though. So why show it that way? By the way, how would you make this the trans diol? I'd make it from the epoxide. And maybe like H3O plus. Yeah. Mechanism, protonate your epoxide. Right? And then water attacks, right? Top or bottom doesn't matter. How's it going to attack this carbon?
On back.
Backside? And so this bond would now be back where that would be forward. Okay. Yeah. So epoxide chemistry would give you the trans diol, where this oxidation chemistry gives you cis diol. Okay, this reaction sometimes can give kind of low yields because the diol can be further oxidized. And the big three are strong oxidants. And sometimes this further chemistry will happen here. And you might get low yields. A higher yield can be obtained if you use osmium tetroxide. I don't know what happened to my periodic table. Everybody got a periodic table? It's disappeared off the face of the earth. Where's osmium at? Where's manganese? Okay, same thing. Osmium has one extra electron. It's supposed to have one extra electron. It's very similar, but it's neutral because it's supposed to have one extra electron. The manganese is supposed to have one less, and so when they're isoelectronic, the manganese trioxide is a minus, but osmium tetroxide is all neutral. Okay, you can look at the structure. The structure is very similar to manganese. Previous page, okay? And the mechanism, very similar. 2 plus 3, 5. Okay, it's a cycloaddition. And here you make what's called an osmate ester. And the osmate ester is actually stable. It can be isolated. It will not spontaneously break apart like the manganese ester. To cleave this, you can be cleaved to the diol. It will be a cis diol, but it takes a reagent, either hydrogen peroxide, which is an oxidant, or sodium bisulfite, which is actually a reductant. And we're not going to look at the details here. This we can call magic. We had a magic step in organic 1, right? What was that for? Hydroboration, the oxidation was magic. Well, this is a osmium reaction and oxidation or reduction. It's interesting. Again, it's sort of a predictive product reaction. Okay. It's an alternative to KMNO4 for converting an alkene to a bicycle diol, but you tend to get better yields. The osmium is more selective. Problem is, osmium is quite toxic. Okay? So here's your dilemma. Do I want a better yield, but toxic? Or is it okay to get not as good a yield, but to have a safer reagent? You make the decision. All right? You can probably look up osmium tetroxide on the wiki, and it'll probably say it's quite dangerous. right? But it is an alternative. Okay, I need to do some practice here, particularly with sort of open chain. It's going to be a cis diol. Got to be careful though. Cis. We can go backwards. What starting material might you use to make guaifenesin, which is a common decongestant? Well, what starting material would react here? Because then you could come up with a variety of reactions. What starting material? Take a look at that. Questions like this. Chance to go back and look at Fisher projections. Stereochemistry. Again, because if you're doing a ring, it's much easier to deal with stereochemistry in a ring because it's sort of fixed. The one below you need to think about a little bit. We'll look at that. And then we'll look at the rest, including ozonolysis. Okay? Using ozone. One of the top 10 reactions in organic chemistry. There's about 15 or 20 top 10 reactions. Okay, guys, see some of you, we're going to meet upstairs in lab. We'll get the reaction going, then we'll go downstairs. Also, your lab report due from last week. Everybody good?